Good afternoon, everybody. Today we have another short webinar about a code which is developed under the Space Center of Excellence. So today you will hear about the kinetic approach to simulating plasmas using iPic3D. And we have two tutors from the Catholic University of Leuven. It's Fabio and Pranab, who will take over from me in a bit. And today's agenda is to address researchers interested in particle in cell methods and high performance computing. The tutors will highlight pros and cons of the particle in cell methods and their applicability in astrophysical environments. And there will be a discussion about the recent and planned improvements to the code as well. So with that, I will pass the speech to the first speaker, which I suppose is Fabio.
Okay, yeah, I'll go ahead then. Indeed, this webinar is on iPic3D, which is a code that's included in the space collaboration or Center of Excellence, however you want to call it. So yeah, as usual, I have trouble with the Zoom covering a large portion of my screen with its toolbar. Okay, I'll try to put it out of the way. Right. Essentially, we're talking about this Center of Excellence space, scalable parallel astrophysical codes for exascale. The running time is between 2023 and the end of 2026. It is a European collaboration that involves 15 partners from 8 countries. And there are research institutes, including indeed KU Leuven, which is where Pranab and I are. It's coordinated by the University of Torino, by Andrea Mignone. There's also computing centers that help on the way, including Cineca in Italy, IT4I in Prague, Barcelona, and HPC companies actually involved with the development of several codes. The idea here is really that essentially the COE aims to prepare astrophysics and cosmology applications for the transition to exascale and beyond. Essentially, you know, if we talk about the newest computing technologies, we are talking about superclusters that are ready or nearly ready to do exascale computations. And that means that if the clusters are available, we also need codes that can effectively exploit such large infrastructures. That's not obvious because codes that work on supercomputers tend to degrade in performance as you go up in the number of processors that you use. On top of that, the newest clusters employ technologies that go beyond the classical processors or CPUs, and that rather rely on GPUs, so on video cards essentially, to do calculations much faster. But codes that are used in scientific research, especially in astrophysics, are typically not ready to exploit either of the two, not the exascale machine and not the GPUs. So the idea for space is really to evolve a number of codes, 7 codes, that already exist and have been used in astrophysics for many years into new products that can exploit the new machines under the Euro HPC joint undertaking, or JU. So yeah, space pursues this objective not only with scientists, but also with co-developers, HPC experts, and hardware manufacturers and software developers. So it's really more than just the typical science collaboration. And yeah, essentially, we want to put together a number of people who are already working on these things sort of in a scattered way, such that this is done in a more organized way, I would say. All right. Let's talk about iPic3D specifically, which is a code developed at KU Leuven. iPic3D, as a name, it involves a number of acronyms. Let's break it down to pieces. So iPic3D means implicit particle in cell and then 3-dimensional. It is the last code in a long descendants of fully kinetic codes. What does that mean? I'm going to explain it in a second. But essentially, they have been used, this descendants of codes has been used for many years to carry out numerical simulations of what we call collisionless plasmas in astrophysics on supercomputers. And the target of these specific codes is the multi-dimensional plasma physics, encompassing a number of characteristic physical scales, from what we call the particle scale, so scales at which individual charged particles, such as, let's say, electrons and protons, live, to what we call macroscopic scales, scales that are really global. You see here a depiction of, for example, the Earth traversing what we call the interstellar medium, the plasma, this collection of charged particles that fills the heliosphere, the region of space around the sun. And you see here a bunch of magnetic field lines also represented with this gray color. The microphysics, the kinetic particle physics, happens at very small scales. And then there is physics that happens at what we call, again, macroscopic scales, the scales of the whole, planet in this case, or magnetosphere of the Earth. These scales are also called fluid. And essentially, to have a more intuitive view on this, you can just think of when you talk about water. The water is made of individual molecules, but typically when you look at water, you don't see the molecules, you see sort of a collective, macroscopic flow. If you were to zoom into the water, you would see the individual molecules, but typically that's not how you describe water. You don't need to describe, each single molecule by itself to describe the overall behavior of water flow. That's essentially the same that we're looking at here. We can describe plasmas, we can describe these collection of charged particles from the particle or from the fluid perspective. And based on the description that you choose, you will get richer physics, essentially. The particle description is richer, but it's also more difficult for the reason that I gave before, which is indeed that you have to describe each particle individually. The unique feature of iPic3D specifically as a code that simulates, plasma particles individually, is the fact that it uses semi-implicit methods. What this means, I will explain in a second. Just as a heads up, the code is publicly available on GitHub, which is actually one of the objectives of SPACE, to have the codes on public repos. Okay, so more details into the physics we're talking about. So what you see here is sort of a representation of the physical equations we are considering. To describe the plasmas, to describe these collection of charged particles, you need to describe first of all, electromagnetic fields. Electromagnetic fields are important because plasmas are charged collections of charged particles. If they're charged, then they respond to electromagnetic fields. So electromagnetic fields are here on the left with Maxwell's equations, the classical set. And then, depending on the scale we're talking about, I already mentioned this, you can look at plasmas from, again, particle point of view or fluid point of view. The particle point of view tells you that each individual particle moves in space according to the classical equations of motion, which are, the derivative of position is velocity, and the derivative of velocity is acceleration, in this case, acceleration due to electromagnetic fields. In the solar environment, we are talking on, the particles live on scales which are given here sort of indicatively with these numbers. They live, the particle phenomena, really, the kinetic plasma phenomena, they live on scales that range between, let's say, 10 meters, really, and let's say 1,000 kilometers. At these scales, the individual particle behavior is still important. If you don't describe it, you don't capture some important phenomenon. Then if you go at very much larger scales, 10,000 kilometers or 1,000,000 kilometers, then again, like the water I mentioned before, you don't really need to sort of study individual particles to still get a good picture of what the overall plasma flow does. And then what you can do is you can resort to another set of equations, which is Navier-Stokes equation, which are here on the top. And these equations describe plasmas from a collective point of view. You see that there's a symbol here that is rho, which represents density. One single particle doesn't really have a density. It doesn't make sense to talk about density for one particle, like in this case below. But in this case, we're looking at collections of particles altogether, and then it does make sense to talk about density, just like it makes sense to talk about pressure and current and bulk velocity, etc. What you do in astrophysical codes is you put together these set of equations. if you put together Maxwell's equations with individual particle equations and you solve these equations together, you get what we call the kinetic physics of plasmas. And if you put together Maxwell's equations with Navier-Stokes equations, what you get is what we call magnetohydrodynamics. These are two descriptions which are, complementary in a way. This one is more fundamental, but it's also more difficult because, again, you have to describe individual particles one by one. Also, the applicability of these methods is different. For individual particles, you're going to look at stuff that happens at small scales, small length scales, and fast time scales. And also for plasma that we call collisionless. Collisionless means that individual particle-particle interactions are very unimportant. And instead, in this other limit, in the fluid limit, you look at scales which are large and slow, and you look at plasmas which we assume to be collision dominated. Essentially, that binary interactions between particles are very important. All right, so what iPic3D implements is the former kinetic physics models. Okay, it's a fully kinetic model. And we do this by employing a numerical method which is called particle in cell. It's a numerical method to solve the equations I showed you before, these equations, Maxwell's equations here on the left and the particle equations on the right, to essentially simulate plasmas fully kinetically. You need to simulate all the particles individually. And okay, I wrote here, the relativistic version of the equations of motion, but it doesn't really matter. They are the same equations even in the non-relativistic limit. There's a large number of codes available on the market. They all sort of work in the same way. Essentially, what you do is you solve the field equations on a grid, on a numerical grid. You solve the charged particles, the charged particle motion individually, and you make particles and fields communicate by giving the fields to the particle equations and by collecting the source terms of Maxwell's equations from the particles. The source terms being, the charge density and the current. And so each particle in cell code is always structured sort of in the same way. There's 4 steps where one of the steps is, solve Maxwell's equations again on the grid, then give the fields to the particles to evolve the particles via solution of the equations of motion, and then collect the source terms from the particles to the grid, as I said before, and then repeat in a circle once or more times per time step. You have a time evolution of both particles and electromagnetic fields. That's the gist of it, right? This is the general scheme for a particle in cell or PIC code. There's many in astrophysics that are used, I think order of tens. They're all good. But what I'm highlighting here today is the difference between explicit and implicit particle in cell codes. So I showed you, a set of equations that needs to be solved together, and I showed you that there's a field part and there's a particle part. Now the question is, how do we do it to make it, practical? Well, there's several ways to do it. The most straightforward is to simply take the explicit approach and say that I see myself at some time level n, let's say. What I do, I first do the particle push, then I do the field advance that I showed you in the circle before, and I am, with all quantities at time level n+1. However, I can also do a different thing. I can also say I am going to solve these 2 sets of equations, not one at a time, not first one and then the other, but actually together. And then what happens is that if you look closely at the set of equations you have, you realize that they are a full set of non-linearly coupled partial differential equations. And then the only problem with this, the big problem with this, with having this gigantically coupled system is that you have to solve all these equations together at the same time. And the only way to do that is to use an iterative method that tries to find the solution iteratively by minimizing some error. And this takes a very, very long and hard effort to converge to something before you can go to the next time step. This is called the fully implicit approach, where you solve all these equations together at the same time. Now, what we focus on in our code is the semi-implicit approach, in which we say, okay, let's make things a little bit less complicated than this. We are going to solve the particle push first, and then we are going to actually solve the field equations in a slightly more advanced way. that still requires iteration, but it's an iteration that only involves the fields. So it's easier than the full implicit approach. And why would one choose to do, things such complicated if you can just do what I show you here on the left? I'll get to that in a second, but just to give you a tiny bit of an idea of what we're talking about when we talk about implicit methods, this is the set of equations that are solved in iPic3D. First you solve the particle equation of motion for the position, you advance the position of the particle. You can do this explicitly because stuff at, time level n or time level n minus 1/2, you already have. And then this is the big monster that we have in our code. This is a one system of equations in the unknown electric field. It is a big system of equations of size, number of grid points that you have in your simulation. And then the whole point of doing things with iPic3D is that you have here on the right side a function, J, which is the current, which you can write as an explicit linear function of the electric field. So this whole system of equations is a linear system in the unknown electric field components that you can solve with a linear solver. That's relatively easy on parallel computers. And then once you have the new electric field, you can update the particle velocity like so with the new electric field. Also, explicit solution, that's easy. So why, again, this is a bit more complicated than just straightforward solving of set of equations. So why would we want to do it? Well, explicit schemes are easy to implement, as I said before, right? You solve Maxwell's equations in a sort of explicit way. The particle equations also explicitly. This is all easy. These are, fast codes. They're easy to implement and they're also cheap to run. However, the problem is that explicit PIC codes bring in what we call numerical instabilities. Essentially, your code is going to solve the equations, but if you're not extremely careful with numerical parameters, then your code is going to solve your equations in a very wrong way. It will produce unphysical results. These results are useless. They can't be interpreted to extract physical insight, really. They are garbage, numerical garbage, caused by the fact that the numerical method, the way you're solving your equations, is not good. Now, if we turn to implicit schemes or semi-implicit schemes, then what happens is that, you need to solve Maxwell's equations implicitly. You need to solve particle equations, explicitly or implicitly if you do semi-implicit or full implicit. And this is hard. And these codes are slower. However, these methods are stable. You will never, if you're careful with your parameters, you will never have the instability that explicit methods bring. And so your results will typically be much more reliable, will typically be much more physically relevant because those instabilities are suppressed. The other nice thing about these methods is that actually they are capable of conserving energy exactly inside the simulation. In nature, energy conservation is a fundamental truth. But when you solve equations numerically, nothing tells the computer that energy should be conserved inside a closed system. And so typically explicit methods don't conserve energy, but implicit methods can. And this happens, it can be enforced. And so that's, something that we like very much because we believe that solving things implicitly and conserving energy is, more adherent to reality. All right, just to make an example of a very simple test case, what I'm showing you here is a very, very simple test where, what you see here at the bottom left is the phase space distribution, space versus velocity distribution of individual particles of different species. In particular, you see protons in blue and electrons in red. What is happening in this system is that from the beginning of the run, you are making two beams of particles collide with each other. When you do this, you create what we call a shock. You create a sharp transition in properties of the plasma. And, there is very rich particle dynamics that goes on in these cases. There is, particle reflection at the shock front. There is energization of particles. Particles can pick up energy, essentially, becoming potentially even relativistic, So it's very rich dynamics that happens all the time inside the heliosphere that actually has real impact because energetic particles can be created throughout the heliosphere and potentially penetrate the atmosphere of the Earth, the magnetosphere of the Earth, and even impact on our own technology. So being able to simulate these phenomena is very important. This is a very simple, one-dimensional setup, which is just an example. But what you see here on the right, without looking at labels and without really looking at what these different lines are, is a measure of energy conservation in a typical particle in cell simulation. The blue line is an explicit method, is an explicit run. And in this metric that I'm giving you on this plot, a flat line would mean energy conservation, and everything that's not a flat line is energy non-conservation. So, explicit blue line, you see very clearly that energy is not conserved. And the implicit in this case is this orange line. Well, it's pretty flat, so energy is conserved pretty well, which is it's a whole world of difference between the two simulations. If I'm looking at this thing and I'm trying to predict how much particles energize, for example, because I want to know how dangerous it is that a solar storm is bringing particles into the magnetosphere of the Earth, then I need to be sure that the energization that I calculate is correct. Implicit methods can do that for you. Another test case is a very typical reconnection setup. Magnetic reconnection is a physical phenomenon in which magnetic energy that is stored, in large-scale magnetic structures can be converted into particle energy. So once again, we're talking about a mechanism of an energization of plasma, which relies on the fact that magnetic fields can be dissipated and converted into magnetic energy can be converted into particle energy. It typically happens, as you see here at the bottom left, in terms of spatial distribution of field quantities and density, plasma density, and current. I think in this case you're looking at plasma density. You start with what we call, current sheets. You start with basically plasma flowing and creating some currents in a sort of ordered way, and then naturally over time these current sheets, they break apart, they reconnect, and they create these giant balls of plasma that we call plasmoids. These balls of plasma is where the energization happens. This is a two-dimensional simulation that basically recreates this phenomenon on a computer. And on the right here, I am again plotting some energetic diagnostic in which I'm actually plotting the total energy inside the system, and then the division between magnetic and kinetic energy. The blue line is magnetic energy. As you see, it goes down. And correspondingly, the kinetic energy of the plasma goes up, which means, and the total energy is pretty flat, which means it's pretty well conserved. And this measure really tells you that, magnetic energy is flowing into kinetic energy. The nice thing about all these the two simulations that I showed you so far is that I am systematically, severely violating the instability conditions that explicit codes would impose to your simulation. Explicit methods would impose that you use, for example, a much, much higher numerical resolution, that you use much finer grids, many more particles, to respect some instability conditions, to have physical results. But I am violating those conditions very strongly with these simulations. And the reason why they're not exploding is because I'm using an implicit method, which can handle that. The result is my implicit simulations can use many fewer grid points, many fewer particles, and produce results which are still physical. This is very important when you do calculations on computers, because you don't want to wait for years before you have a result. And especially if the reason why you're waiting for years to have a result is that you're only imposing very strict simulation conditions, because otherwise your method is unstable. So here's the thing, like with implicit methods, we can just do things faster. We can, simply speaking, do things much faster than typical methods would allow you to. All right. Now to connect to the, to space, I want to just give you an idea of what it means to do kinetic simulations on supercomputers. When we talk about doing simulations on supercomputers, especially for astrophysical stuff, we typically consider to essentially distribute a simulation domain, such as this one that you see here which actually produces a shock in 2 dimensions. We talk about distributing this domain onto many processors. Sometimes hundreds of thousands of processors, really, depending on how big your simulation is. In kinetic simulations, where there is a grid and where there are particles, what happens is you typically use MPI domain decomposition. It means that you take this system, this physical domain, and you divide it in little blocks. Each block you give to a different CPU, and each CPU will work in parallel with the others, and that's how you can speed up a simulation. Instead of letting the whole simulation be handled by one CPU, you split the whole simulation among several CPUs. The composition of the domain can be done also based on particle load. If I have, on top of having a grid to divide on processors, I also have particles. What happens is that maybe I have many more particles in one region of the domain than in another one. For example, let's look at this shock simulation here. What you see here in color represents density, which means that on the right-hand side, on the right half of this domain, there are many, many more particles than on the left-hand side. So now imagine that we are dividing this simulation among processors, and imagine that we are dividing this among processors in a sort of, by creating little squares. If I create little squares of this domain here on the left-hand side, or here, I expect, of course, this part of the domain to contain, in each subdomain, many more particles than in this part. And then what happens if I do that? What happens is that the processors that are found here, they will have to handle many more particles than here. So they will have much more work to do than the processor here, which means that basically these processors will be done very fast and these processors will be done very slowly at each time step. This is called load imbalance. It's a typical problem in simulations. How to avoid it? Well, I have to be smart in how I do my domain decomposition. Imagine that now, instead of dividing this domain in little squares, I divide this domain in stripes, horizontal stripes. 1 like this, 2 like this, 3, etc., etc. If I do that, then each processor will handle a whole stripe, and each processor will sort of have the same amount of particles, really, because it will handle both a region with fewer and a region with more particles. So this is why I write here, that the domain decomposition is done based on the particle load to avoid load imbalance. More advanced than this, there is a thing that we call, adaptive load imbalancing, where actually processor can be rearranged throughout the simulation very dynamically by themselves, or even what we call AMR, adaptive mesh refinement. Adaptive mesh refinement means that, maybe in a certain region, you want to capture things better than in another one. So what you could think of is refining your numerical grid in a certain region and not in another one. This is done in astrophysical codes, but it's very hard. And especially for a particle in cell, this is extremely hard because it itself introduces numerical instabilities. So this is rarely implemented, and when it is done, well, you have to be very careful. So the state of the art of kinetic simulations on supercomputers is adaptive load balancing, redistributing particles across processors dynamically. And then also there's OpenMP threading, which within the same processor to vectorize operations and do things even faster. Now, recently, this has been done, the simulations of particles can have been done also on GPUs. And so recently, the interest of people who do kinetic simulations was shifted towards using GPUs. Using GPUs, why? Well, GPUs, are essentially, each GPU is a collection of thousands of processors. So each GPU could handle, for example, many particles at the same time, if you will. So that's what's been happening recently, and that's also a big motivation for space. However, how to best implement parallelism in particle codes, that's not straightforward. The presence of particles and also a grid offers opportunities for parallelism, as I sort of already said, right? However, one also has to be careful to consider that different numerical methods, different types of PIC codes also offer different compatibility with new technologies. If we look at this thing here at the bottom left, you see an example of the adaptive mesh refinement that I was mentioning before. In this simulation, You see here, there are regions where the grid is refined and refined and refined adaptively. That's why it's called adaptive mesh refinement. It is dynamically refined throughout the simulation. That's really cool because then you can concentrate resolution only where you need it and avoid to waste resources. However, that's very hard to implement. And if you want to do it in an implicit PIC, this becomes almost impossible. In particular, implicit PIC codes such as iPic3D are also more difficult because they have a little bit of a problem with GPUs, which is the field solution. As I showed you before, the field solution, the electromagnetic field equations, they are solved in an implicit way. But this requires local iterative operations and especially a lot of memory to do global communication across the processors to solve the field iteratively. The solution to this problem is that actually you should not do the field advance on the GPUs if you're trying to implement an implicit PIC code on GPUs. The reason is that if you try to do that, the GPUs will not have enough memory to handle the field solution. So implicit PIC has been ported to GPUs before, and the way this was done was by essentially keeping the field solver on CPUs and then distributing particle batches on GPUs, many GPUs at the same time. So basically, in the 4-step cycle that I showed you before, you would do 3 of the steps on GPUs and 1 on the CPUs. That's the best way to port an implicit particle in cell code to GPUs. Now, as for what the state of the art is in terms of performance of particle in cell codes on HPC clusters, these are a few scalings examples of existing particle in cell codes on different clusters. Again, it's sort of not useful if you try to absorb all this information at once, with all these numbers and these lines. Essentially, what I'm showing you here is performance of a particular particle in cell code on a particular cluster when I increase the number of processors. The reasoning is very simple. If I run the same simulation on twice the amount of processors, does my simulation take half of the time that it took before? If the answer is yes, then it means that your code is scaling well. It has a good scaling behavior. If the answer is no, then your code is not behaving very well. And the problem is that then if you try to use many CPUs, your code will degrade in performance. It will, basically at some point, what happens is that I use more CPUs, but it takes me longer to run a simulation. That's the point where your code is really not behaving well. So in all these plots, regardless of what these metrics exactly are, what you want to see are flat lines. Sorry, not flat lines, but actually straight lines. If your line is straight, then your code is behaving well. If your line is not a straight line, either horizontal or inclined, then your code is not behaving very well with respect to the number of cores, which is on the horizontal axis. Now, in this case, in the case of this central picture, the code warp X, which actually uses adaptive mesh refinement, won the prestigious Gordon Bell Prize in 2022, which means that they got the best possible scaling of all the codes involved in the competition on several clusters, several superclusters, including some of the biggest superclusters in the world, Frontier and Fugaku, etc. So they won a very, very prestigious award for being able to make their code scale very well. I already showed you this cycle, and I already sort of highlighted these 2 points. Solving particles in an implicit PIC code on supercomputer is relatively easy to have, good scaling properties if you're talking about the particles. The particles themselves, each single particle lives on its own. It does operations on its own. So I can literally just divide my particles across processors and the scaling will behave well. Each processor will just increase the number of particles, but I use more processors. No, that's fine. However, the field equations to be solved implicitly, that's the scaling bottleneck. So that's the whole point of the difficulty of porting a particular particle inside code to some technologies such as GPUs, etc. As I was saying before, this has been done. I already showed you this picture. The strategy was to keep the field solver on the CPUs and to keep the particles on the GPUs. And if we look at this plot on the left, now this is a measure of performance of implicit PIC on CPUs and on GPUs. All right. This was done by the group of Stefano Marchidis at KTH in Sweden. And what they did was, they ran iPic3D on CPUs and they got a certain amount of operations per second. That's the sort of what this metric here is on the left. Amount of operations per second. If I increase the amount of operations per second, then it means that I'm increasing the speed of the code essentially. With the CPU version of the code, they got some amount of operations per second. With GPU version of the code, they got well, factor of over 10 when it comes to speed up by doing this porting that they did. So it is possible. And that's what actually space aims to do as well in a more, I would say, modern way. This was a simple experiment done with an example code. What we aim to achieve is sort of the same, but with a production code, with a code that can actually run on many GPUs and do real science. Real science, such as the one that I mentioned before, reconnection. We can, for example, take the example of magnetic reconnection in the solar corona or around black holes or in many astrophysical environments. As I said before, this is a mechanism that liberates energy, magnetic energy, and converts it into particle energy. This is an example of the current sheet that I showed you before, but in 3 dimensions, actually. The problem of doing very large scale reconnection is that there is a very large scale separation between the macro scales, the scales of, let's say, the physical object you have in mind, and the single particle scales. But reconnection is essentially a kinetic process. So you really need to capture ion and electron scales. So you really need a PIC code. A PIC code that is capable of capturing all these scales. So you really need many particles and you really need very large grids. The GPU technologies can offer some, let's say, 10 times speed, which is what we need to go to the next, well, to really push the state of the art, if you want. All right. Now let's talk about iPic3D in the context of space. As I said before, there's a number of reasons why we want to achieve very good performance of a PIC code such as iPic3D on GPUs. The objectives are the following: deployment on the JU clusters, porting to GPUs, and then scaling to system size, really scaling to as many well, GPUs as we can. To do this, we are actually working with KTH, which includes some of the original iPic3D developers from 15 years ago. So there's a clear advantage of synergy there. The code is already publicly available, as I said before. The code has been deployed in its CPU version, actually a completely rewritten CPU version, on 7 out of 8 of the superclusters of the JU. In its GPU version, it's being deployed. It has, we have access to those clusters. We are now starting the deployment process of the GPU version. I showed you some of these plots before, right? I told you that when we talk about scaling, what you want to see is straight lines. So here are the performances of the CPU version of the code on 7 clusters where it's being deployed. All the straight lines are good. Blue line straight means good performance. Something that's not straight line is less good performance. Well, in all these cases, you can already see, without even reading numbers, you can see that the scaling is actually pretty okay. This metric is, to be more specific, this metric is really a measure of the speed up. When you double the amount of cores, what kind of speed up do you get? If you get a speed up of 2, then your code is working perfectly. Typically, we get less than 2, but actually, you know, we're pretty close to this 2 factor. Specifically for 2 of these clusters, we actually ran what we call a weak scaling. Again, straight lines are everything you want to see in these plots. And in this case, the type of scaling is slightly different. What happens in this case is that you actually, you do it in a sort of different way. And what you measure is what we call efficiency. You know, efficiency means that basically I keep the same system size. Sorry. These were strong scalings, and these are weak scalings. And in this case, sorry, just to rephrase, here we're measuring the speed up of the code. Really, I increase the number of processors, and I get, you know, a speed up. In this case, I measure what we call the efficiency. Really, so it's a completely different. Sorry, not a completely different. It's a very related metric. That, you know, if your code scales perfectly, you get 100% efficiency for as many cores as you can. If it doesn't, then this efficiency decreases. But you see that in these 2 cases, it stays very close to 100%, stays above 90. All right. Okay, so I guess just as an overview of the activities of space for iPic3D, the timeline in which we're going to work is the following. We are now, you know, compiling and running the GPU version of the code on different clusters with NVIDIA GPUs. The GPU version of the code that we have is written with CUDA, but you know, we have under development a support for HIP in collaboration with KTH, so that we will be able to deploy this on different types of GPUs. And then essentially, the next steps will be to actually improve the numerical method that is implemented in iPic. On top of what we have already, which is a semi-implicit method, we want to implement a new numerical method that, you know, conserves energy exactly. I mentioned this is possible before, but it's not possible in all implicit methods. The one we have doesn't really do it, but we can implement one that does, and that's what we're going to do. And then we're going to also implement the relativistic version of the same method in order to look at relativistic phenomena. These are important, you know, when you go to things like black holes, for example, reconnection happens around those objects. You need relativity, because relativity, you know, particles can go very fast, so relativity is involved. You're basically talking about typical speeds of order speed of light. This is our timeline. We have, you know, we have already started within the context of space. We have a few steps, including scaling plots, validation, preliminary results of HIP, implementing the energy conserving method, you know, defining scientific cases for the new method when we have it, include improvements, and insert the, you know, the relativistic method. Yeah, to be continued. I guess I can close with my slide on acknowledgement and disclaimer, which we have in all our space presentations. I hope I gave you a sort of like comprehensive overview of what is happening with iPic3D in the context of space. That's all I wanted to say, so I'm gonna be happy to take any questions if you have.
Thank you for the talk, Fabio. And in the meantime, we would also like to ask you, as usually we have the satisfaction survey, so if you could just fill it in for us, the one with many people, so we will appreciate any feedback on the talk and generally on the space COE training needs, or if you wish us to add some topics to the agenda, then this would be your chance to let us know, and we will really appreciate it. And thank you very much for coming for this tutorial, and thank you, Fabio, for the talk again. It was very nice, and I hope to see you at the other. We have one more left, which will be held on 15th of October, so in like 14 days from now. So thank you very much, and have a nice rest of the day.
Thank you. Bye-bye.
Bye-bye.